Good morning to all of you. Thank you for taking your time to come for this presentation on how good is my design. We hope you would be in a position to hear us clearly and get started. If you are having issues with regard to this presentation, audio or the video, please inform us in the chat mode. Otherwise, we'll get started. Okay, this presentation is about the best design practices that we can employ when it comes to designing products in our office. My name is Natarajan. I represent AGS India. We hope you enjoy this presentation. The agenda of this presentation is to look at the design process overview, followed by the requirements of the end customer from whom we are developing the products, coming up with design specifications that is translated from the customer requirements, followed by case studies of actual projects that either customers have done or we have done as a part of our engineering services in understanding the customer requirements and addressing the issues that come after the product has been launched or in the pre-product stage. Then summarize it with a checklist of good design practices and the benefits of approaching this in this way. Now, when we look at the design process overview, all designs have to start with the quality objectives as the initiator of the design process itself. The DFQ objectives or the design for quality objectives as measurable specifications can be classified into under two different aspects. One is called as the assembly objectives and the other one is called as the performance objective. The assembly objective relates to integrating the product components together in a design for assembly, providing the datum reference frames, the tolerance analysis, the tolerance optimization, and producing the key characteristics when we are releasing the drawing. The other aspect which we are here today for is looking at the performance objectives and how we can integrate the design failure modes and effects analysis, the design for manufacture, the design for cost, design for service, design for transportation, performance, and life as a part of our drawing release practices so that the fit, form, and functional requirements of the design can be easily captured in the design intent and translated into the product that we manufacture. So this presentation is going to be about the aspects that are shown in the red on the design process overview. In other words, intrinsically, any design which protects the design for quality objectives while keeping in alignment with the manufacturing requirements, the life requirements, the design for performance, the packaging and transportation, service, and the cost as attributed to the end customer will always succeed in terms of good and efficient designs. So when we translate the customer requirements, first when we look at the customer requirements, customers are always looking at superior performance. They are not looking at affordable cost. They are not looking at low cost. They are looking at affordable costs. Recyclability, environmental friendly aspects of designs are gaining forth. Warranty protection is a major issue. Our competitors are giving additional warranty for a lower cost. And at the end of it all, once you have sold your product, the highest customer satisfaction is what gets you the repeat business from your customers. So the customer requirements with regard to these 5 aspects need to be taken care of in our design specification for our products to succeed. The current state of affairs in any organization can be summarized based on what you see in this picture. We test the designs. Design is always worried about whether the design would succeed in testing, whether there would be any issue with regard to the product recall, rework due to performance, and other aspects which directly attribute to design, adding up costs to the company either in direct form or indirect form. Visualize the iceberg where 1/10 or 1/11 of it is exposed outside and the rest of it is hidden underwater. When we are looking at the costs attributed to the company as a result of the product, 9 out of 10 times the attributes are directly related to design, either in terms of incomplete specification or because we released the product before we could have tested it at our place fully. To overcome this, the expectations from the design department is always challenging. People are looking at ways and means to get their product designs right the first time, ensuring trouble-free performance either in the test or at the customer's place. Robustness of the design is what we are looking at. Extended life and warranty is always an issue. Giving least cost alternatives to the design, from design to the marketing and sales, is always helping us to translate design proposals or product proposals into orders. And last but not the least, we always tend to provide designs for abuse. Gone are those days when designs needed to be provided for abuse. We need to provide foolproof designs and not abuse-proof designs. So when we look at the design specifications, when we are putting a product together, the failure modes that we are trying to escape or we are trying to protect our designs from, our products from, come foremost in terms of the specifications that we need to put with regard to the design that we are developing. These failure mode information could come from past data, which include service data from our service department, or it could be from lessons learned from other people or competitors whose products we are looking at in the marketplace, getting market surveys, either about our products or about our customer competitor products, and looking at the failure modes and enumerating them. So the first and the foremost in any design specification, when you start with the statement of requirement, it comes with the fulfillment of the DFMEA, which is coming in the next slide. Then looking at the factor of safety, estimation of life, efficiency improvement, alternate design for least costs, and sustainable designs. These are important aspects that find their place in the design specification when we are coming up with the statement of requirement for a particular design. The innovation that comes in a design is private to the company. There are 3 different kinds of designs that we can come up with. One is called as derivative design, where we take a design, change a few dimensions here and there, and produce a new design. The second one is called as evolutionary design. Evolutionary design is nothing but starting with the basic design which is already there and coming up with a transformation of the design which could end up with a completely new design, but the current design from where you started forms the basis of it. And the third one is the innovative design. Derivative designs and evolutionary designs are always challenging when it comes to the companies to maintain their profitability. Derivative designs, companies which do only derivative designs would be unsuccessful in the long run. Evolutionary design companies would exist, while innovative design companies would always conquer the marketplace, keeping their profitability enhanced, if not intact. Now, incorporating the design process. When we look at incorporating the design process, you are looking at the all familiar CAD interface over here. You see the design binder in which you look at the design journal which comes up with the design specifications and the calculations. And then you have the design validation document, the design for assembly document, design failure modes and effects analysis, design for Six Sigma if you are looking at quality beyond conventional designs in terms of tolerances or in terms of the processes. And last but not the least, the process capability that exists in our shop floor or in our supplier's place. When we incorporate this as a part of the assembly document, we are intrinsically integrating the design process that I have shown earlier so that good practices in design come about. How good is my design is in evaluating ourselves versus these best-in-class practices. So when we look at the DFMEA layout as given in the next slide, you will see it's typically like an Excel sheet which would give you the description of the failure modes and effects analysis, sometimes including the criticality analysis, the severity assessment, the probability of failure, the detectability of failure, and putting this document together which would form the basis for what has been considered in the design and what has been addressed and what are the risk priority numbers for that as compared to what are not being considered. This document is the IPR of the organization. So we write down each and every failure mode as is given in this slide. Give the severity on a scale of 1 to 10, the likelihood of the potential causes, the detectability, the risk priority number, and the response plans and the tracking. This information, when put together as a part of the design process upfront, helps us to refine the designs and assess the capability or the lack of it of the designs. The efficacy of our product is exposed upfront at the design phase. Design validation necessarily has to adhere itself to the DFMEA. Sometimes people call it as the DFMEA, which is nothing but design failure modes and effects criticality analysis. The 10 steps in DFMEA is reviewing the process or the product that we come up with. In this case, the product, because it's design. Brainstorming the potential failure modes with marketing and sales, with service department, with past product data, competitor information, market survey, so on and so forth. Listing the potential failure effects of each failure mode forms the step number 3. Assigning a severity ranking for each one of them, step number 4. Assigning an occurrence ranking for each failure mode, step number 5. Assigning a detection ranking for each one of them, step number 6. Followed by calculating the risk priority number for each effect, prioritizing the failure modes for action, taking action to eliminate or reduce the high risk failure modes, and then calculating the resulting RPN or the risk priority number as the failure modes are reduced or eliminated. These 10 steps are absolutely critical for the success of any product design. Failure to adhere to this process in the beginning of the product specification would force us to revisit this either during the trial phase or during the product launch phase or the customer feedback phase. Irrespective of which time it comes in, a failure mode predicted and fixed at the design stage costs us nothing, almost nothing, as compared to being reported after we have prototyped it and tested at our place, or from a painful market feedback which comes subsequently down the line. So the design validation objectives as a part of design starts with sizing, the weight considerations reflected in the cost, the safety aspects, the performance in terms of deflection, in terms of stresses, in terms of vibrations, in terms of efficiency, so on and so forth. Life, because we keep giving warranty, and then the quality and the sustainability. These are typically some of the parameters, 8 as we can see enumerated over here, which typically would be used by any design department as a part of the validation objectives. Necessarily, these have to be forming a part of the checklist that we put together before a drawing is released for prototyping or tooling. Normally, we look at the factor of safety. The factor of safety is actually a feel-good factor. It is not adequate when it comes to life-based designs. In the 60s and the early 70s, people used to live with the factor of safety as a concept. Subsequently, beyond thereof, people have moved over to life-based designs. It is important that we need to move to life-based designs as compared to factor of safety. Factor of safety does not directly have a correlation to a life expectancy from an assembly or the performance expectancy from the assembly. The factor of safety is a necessary first step in any design evaluation, but it's not the only step. It does not assure our sales and marketing and our company that the product would meet the warranty requirements of the end customer. So factor of safety is feel good. We need to move beyond that into life-based designs. Why? Because cost pressures are there. Every customer is looking for least cost designs while keeping the warranty up above where we can reach. So if we keep on padding it up with the factor of safety in the design department, the company's profitability is threatened, the livelihood of the product is threatened, probably even the company. So factor of safety is one of the aspects. It is, as we can say, a necessary but not a sufficient condition for a good design. Design for warranty is what we need to consider. Here we look at the failure modes assessment, estimate the mean time between failures, schedule the preventive maintenance, reduce or eliminate the service cost associated with those failures, the bottom portion of the iceberg, protection from costs of replacement during warranty period. Imagine the iceberg below the water getting bigger and bigger, eating into the profitability, bottom line profitability of the organization. This typically comes from the service calls that we spend from our pocket that the customer does not necessarily spend when we are in the warranty area. The design for performance, we are looking at power consumption, efficiency, consistency in our designs, so that consistency in our products, performance, down at the customer's place, durability, optimal flow characteristics if it is fluid properties, noise and vibration aspects which need to be eliminated, and the power to weight ratio in certain conditions. These are nothing but the design for performance criteria that we need to look at in our designs. The design for manufacture is typically attributed to stiffness, the repeatability in quality, the effects of the tolerance variation, and the process simulation depending on the nature of the products that we are trying to manufacture. If you look at the pictures on the right side, you would see the near breakout condition coming on the 3 fasteners, primarily as a result of lack of inappropriate tolerances or the factor of safety that we looked at in the nominal dimension, which we did not consider when we were looking at the tolerances that were coming in. You look at the next picture, you see the automobile with the oil leakage at the bottom. Every day when we are removing the automobile from the parking lot, if we keep seeing this oil which is dripping down, would we buy this car or the two-wheeler for that matter? These are all some of the things which need to be considered at the manufacturing level. We would consider this as manufacturing defects. But then the next question that comes up is, in design for manufacture, I need a certain flatness tolerance on the component which are mating together to come up with this leakage problem to be avoided. Now if I give those flatness tolerances on the drawing, but I'm not able to achieve it in the manufacturing process, is it a design problem or is it a manufacturing problem? When you look at the stiffness which is coming up front in the first list of items in the DFM, that's where the culprit lies. We will be looking at it more down the line. The next one is simple things like sheet metal fabrication, thinning of the components, or injection process simulation, as you see over here, which is looking at the fill time. Manufacturing people are looking at cycle time. Design people are looking at robustness. The pre-stresses that have come as a result of manufacturing is unknown to the design department. These are all different areas in which these tools and technologies help us to develop better products, looking at and visualizing the manufacturing issues and problems up front at the design stage to make sure that first time right becomes a reality. Design for service, accessibility, safety, ease of disassembly, maintenance-free designs are some of the important aspects of design for service. We all look at maintenance-free batteries these days. We don't want to fill the water up or top it up with the distilled water every now and then like we used to do earlier. Why? Because we want maintenance-free designs. Similarly, if we give our design department the challenge that our designs have to be maintenance-free, how would we go about it? These are considerations when we look at in the design as a part of what the customer wants, translating the customer wants into design specifications. Sometimes even innovation comes into picture. For example, zero leak design could be an innovation. Service-free design could be another innovation. So innovative designs is what we need to look at with design validation as a major part of our process to contain the costs that we are incurring after the product has been launched. The design for packaging and transportation is something we rarely look at in our designs. Weight is a big consideration. Overall size and space saving is important. If we are exporting containers worth of our products to the end customer, and if I can package 2 products instead of 1 into a container, your transportation costs just got halved. We had a customer who wanted to put in 3 valves instead of 2 by reducing the flange thickness in the overall height of the product. When we were able to do it, his product cost came down by that much because of the transportation costs. Last but not the least, impact-proof design. We always look at buying mobiles which are impact-proof. If at the drop of a hat, if the mobile drops down and if it cracks the front bezel, we are not going to buy a product of the kind same again, right? Similarly, it applies to our products as well. So if we are looking at fragile designs, packaging and transportation would come back to haunt us. Now let us look at case studies of things gone wrong, things gone right, and how we have learned from past practices so that we can share this knowledge as a part of our design process and move on to produce better products. First in case is a centrifugal pump, the ubiquitous centrifugal pump that we use in the power and process. One of our customers has given a feedback that they are not able to hear us. Could you please confirm whether you are able to hear us? Please. Are you able to hear us? Thank you.
So we are able to hear you.
Thank you. So the centrifugal pump is a classic case where we are looking at if you take the service department data from your organization. For example, this is one data that we got from a customer quite some time ago. If you look at the service issues that we are coming up with, misalignment is 29%, bearing replacement is 37%, Soft foot, which is nothing but the foundation, is 6%. Looseness of components as a result of vibrations is 10%. Unbalance is 9%. Cavitation problem is 2%. 7% is the belts loosening up or the belts failing. If we were to look at redesigning or looking at the design specifications as a part of our statement of requirement, where would we put our emphasis on? We would be necessarily looking at the top 66% of the problems reported by the customers, which are necessarily in the bearings, which are in the misalignment. And if you look at the looseness of components, that is also coming from vibrations. If you are looking at cavitation, that could be a source of vibration. If you are looking at unbalance, it could be a source of vibration. So if you look at most of the data except the belt replacement, which is 7%, the rest of them are coming from noise and vibrations. So if we are able to classify the problems according to this from the service department, that's why I put design for service, our statement of specification and the design validation process becomes even much more better, so that the customer experience with our overall product is enhanced, becoming a repeat customer for our products. Customer is willing to pay more for a good experience. Same applies to gearboxes. If you are having rotating components in gearboxes, vibrations, misalignment, bearing replacement, if you classify the problems that are coming in the gearboxes, you would see that they are coming under two classifications, noise and vibrations. Now this is a classic case. What you're seeing is a crankcase going through a machining operation. The flatness variation predicted by analysis, while the measured value are right there. The customer said the leakage was as a result of lack of flatness not being able to come about primarily because of machinability, maintainability of these tolerances in manufacturing. In this company, the design department said that's your problem to manufacturing. The manufacturing people kept on coming and saying, no, we have given one of the best machines for machining this out, and still we have checked our fixture design, we have checked our clamping forces, we have checked everything, and still we have this problem. It is primarily because of the flatness issue. So what you are looking at is analysis versus correlation, the trend being picked up by analysis and the values of deflections being higher in the analysis as compared to a design as compared to the measured data being conservative, and you would be able to pick this up front. So when we are putting this tolerance flatness on the drawing, we need to ensure that these can be maintained by looking at the stiffnesses with a simple analysis as shown at the bottom right. What does the customer see? The customer sees leakage as an issue, frequent oil replenishment, not a good idea, not a good feedback from our customers. This is another example. It's a classic case where in optics, when you assemble the components together, the refractive index of the glass piece or the optical device changes as a result of the stresses induced. The deflections make the focus go out of centrality, leading to product recall. Imagine a component such as this going onto a spacecraft, and because of the vibrations during launch, not during operation, during launch, the product's refractive index changing, as a result of which the component, though it is physically intact, it has failed in its functional requirements because the refractive index has changed. This is a classic example where things gone wrong, things gone right. Machine tool performance. People are looking at high-speed machining, moving away from 6,000, 8,000 RPM, giving higher feed rates, getting better products out faster. So the vibrations, the frequent breakdown, if we were to look at a machine tool spindle, where would we be looking at from a design point of view? After we have fabricated, put it together, we will be going and checking the vibrations at the bearing locations. Why not do it at the design stage? By doing a simple analysis which is called as a frequency response analysis. Without doing it, the vibrations would not be under control. The product repeatability would not be under control because we do not know which are the tolerances which are sensitive. The problem will keep coming as a problem from our end customers. Sometimes the end customers would live with the product till such time their line becomes obsolete and move on to another machine where they may not even come back to us and ask for a request for quote. Forced to work at lower speeds, reducing the overall productivity. These are simple cases where design needs to be validated as well. This is a very classic case where we worked with a German company, and this company said that they were giving a warranty of 12 years for this product. It is nothing but a calendar dryer used in the textile industry for developing the polyester yarn. When we went through this design and we did the factor of safety calculations and subsequently followed it up with the warranty calculations, we found that the warranty which was given was 12 years, while the product could not have lived beyond 8 years. So the product was failing. The replacement shaft assembly was 12 lakhs per unit, and there were 72 units. When we confronted the Germans with a poor design, they came back and said, we don't do warranty calculations, we do factor of safety calculations. Now imagine the liability that comes with this when they have had to replace these shafts free of cost during their warranty period. This is another example of corrosion or erosion of tubes in a heat exchanger, where we are able to predict the erosion of tubes using the fluid dynamics approach, looking at the impact, looking at the erosion of material, and saying how much more life is left in these components before the tube bundles need to be replaced. It's called puncturing of tubes. If it happens within the warranty period, we as suppliers pay for it. If it is after the warranty period, the customer pays for it. Not a very pleasant experience. So when we are looking at these kinds of situations, tools and technologies are available today for us to look at life prediction and performance upfront even before the first drawing has been signed off. Dust and fume scrubber. We all know that in the power and process industry, we have the American Society of Mechanical Engineers, the American Petroleum Institute, the BS standards, the IS standards, where we come up with the stress calculations according to these standards. The ASME standard is silent about rectangular to circular connections, transitions, as shown in this picture. We found up front that this equipment, which is 25 meters tall, would fail the hydrostatics test and the seismological loading test. Up front in the design, changed the design, improved it, and released it into the marketplace, and this is working in Africa even as we speak. This is things gone right, first time. We always look at blowers in factories. People manufacture induced draft fans, forced draft fans, so on and so forth. Imagine the impeller of a fan breaking down or the bearings needing to be replaced within the warranty period. It is money from our pockets. A simple torsional analysis, torsional vibration analysis. Give me a minute. One of the attendees is unable to hear. We are looking at the fan failure, replacement of the bearings and the impeller, the cost to our company as a result of replacement, especially if the units are going to be 6 in that particular factory. If we had done a simple torsional calculations up front, this problem could have been avoided. So the checklists for good design practices starts with the design failure modes and effects analysis, validation for performance using finite element analysis, predicting the life for enhanced reliability, alternate designs for cost and performance. This is one aspect we need to understand. Customers are always looking at lower costs. If we are able to give a low cost design, an affordable cost design, and a superior performance design at 3 different price points for our products, then customers are able to make an informed decision with regard to the product they choose for the warranty they want. Nobody is looking at cheap products for infinite life designs because these come at either ends of the spectrum. So as design engineers, if we are able to give 3 different designs to the marketing and sales department, then we are giving alternates to our marketing and sales department so that the winnability of orders for our companies are much higher, the probability is higher as compared to giving one product and the customer trying to beat you down with the costs for that product, the price of the product. So the winnability becomes much better as a result of looking at alternate designs and providing options to our marketing and sales department. Looking at design for manufacturing considerations upfront, design for packaging and transportation, which normally we don't look at, coming into center focus, design for service. One of the most important aspects in any design validation practices is to keep a goal. The goal measurable in terms of profitability for the organization. So let us say we come up with, in the design department, a goal of 10% cost reduction in our products. How would we start with? The same thing, the overall cost of the product, not just the raw material and the fabricated and the finished product cost, but also the serviceability cost, the packaging and the transportation costs, the design, the manufacturing costs, so on and so forth. When we look at the overall product cost at 10% lesser, that is adding to the bottom line profitability of the organization. That is exactly where these kinds of good practices in design have been leveraged by companies worldwide in incorporating the best practices in design to come up with affordable and enhanced value of products as customers perceive it. So the benefits of design validation, it increases the design confidence, it improves the reliability, eliminates the errors, reduces the input cost. When you eliminate the errors, you get it first time right. Reduces the input cost, assures superior performance, enhances the product quality, and protects the product safety. So when you look at all these 7 attributes as the benefit, they can be classified under 3 conditions. Commercial, where it is bottom line money to our organization. Social and moral. Legal. Would we buy an air conditioner which consumes more power and our runtime costs are higher? No. Would we buy a design? Would we buy a product where we cannot recycle it? Maybe not. So these are different aspects that we need to look at in terms of designs which would make a commercial, legal and social or a moral case for us upfront at the design stage. A lot of time revisiting a design because of a product issue or a failure is always grueling, especially when it has been reported by the customer. These processes help us to make better products. The softwares which have been used in this particular presentation start with the SolidWorks 3D CAD, the simulation premium module, which includes the basic factor of safety calculations to the warranty calculations to the nonlinear calculations to the vibration calculations, and then the computational fluid dynamics with the flow simulation and the injection molded plastic simulations with regard to the plastic component design. We hope you enjoyed this presentation. We would be happy to field questions from you with regard to the presentation shown just now for the benefit of the rest of the audience. What are all the input costs? The input costs that people are looking at are raw material costs, cost of manufacturing. For example, if we look at a flange in a valve or a flange in a pressure vessel, and let us say we have 8 drilled holes. We reduce the number of drilled holes to 6. Now, 2 less holes have to be drilled, 2 less fasteners in the packaging list, 2 less components in the assembly, 2 less things to go wrong. We have just improved the product cost. The product raw material cost is dealt with by the purchase department, no doubt, but it is based on the bill of material that is coming from the design department. In other words, if I reduce the bill of materials, if I standardize the components, let us say I have 6 different types of fasteners in my model, in my design. 6 different types of fasteners, and let us say there are 80 fasteners in my entire design. Would commonizing the design reduce my cost? We can do an assessment up front and take a conscious decision as to whether we really need to have 6 different inventories. I have seen cases where for a product they have not standardized on a design, they have not standardized on designs, and 20% of the design goes with a luxury design, 80% goes with a run-of-the-mill design. The 20% of the design volume-wise is probably 30%, and 70% of the volume that is being sold is only the not so good design. Why would you want to carry an inventory for 2 different types when you know that the volumes are going to be completely different? So now when you look at the inventory, when you look at purchase replenishing the inventory, you want to keep the inventory and the just-in-time costs low so that your overall product cost comes down. One of our customers, we did a design assessment wherein the department had more than 1 crore rupees worth of inventory for a product which costs 8 lakhs. So when we did this inventory assessment, came back and standardized the components to reduce the inventory, the overall profitability stress that they were going through earlier got addressed. This is another classic example of where the raw material cost or the input costs comes of use. Next question, please. Regulatory requirements provide us with guidelines for designs. Why would we want to do a finite element analysis or any other simulation? This is a good question. This comes in primarily from the point of view of, if you look at the ASME calculation, the appendix for the finite element analysis is getting bigger as compared to the code. If you look at the EJMA standard, the Expansion Joint Manufacturers Association standard, they have moved away from manual calculations onto the finite element side, primarily because for multiply bellows, it is simply inaccurate to put a manual calculation together. Third point, if the same calculation, same standard is going to be used by 3 different suppliers, and each one is coming up with their own designs based on the codes, then what is the USP for our organization in terms of reducing costs at the design stage? while meeting the requirements of the codes. In fact, if you look at the IS 800 code, it simply states frame analysis and finite element analysis is something that needs to be done. In the absence of that, you can use the closed form solutions or the formulae given in this book. And these standards always put a disclaimer inside. This is only a guidance. It does not assure that the design is going to work. So in all these cases, in spite of the codal provisions, analysis of what if conditions need to be done to prevent grief. In spite of the ASME code adherence, in spite of codal provisions adherence, why is our service cost higher? If we answer this question, then we would see that validation needs to be a part of the design process. Okay, volumetric discounts are given for most of the suppliers primarily because of the bill of quantities. Absolutely. When you standardize designs, your cost comes down because you have a much more better buying power as compared to 6 different kinds of fasteners that you would have used on your drawing otherwise. Thank you very much for that point. Is product warranty derived by the design department? As I said earlier, industry has moved long ago away from factor of safety based designs to life based designs. Why? Because life based design throws up a completely different picture as compared to factor of safety, and factor of safety cannot be related to warranty directly. So your fatigue analysis, and sometimes you even do the wear analysis with a spreadsheet, taking inputs from the finite element analysis in terms of the contact stresses, are all indicators where you do the product warranty assessment at the design stage. In fact, it necessarily has to be done at the design stage. If you look at all the equipments that are being manufactured for the Ministry of Defense, or for that matter, the aerospace industry, when we are traveling by flight, they are all life-based designs where after a certain life, the components get replaced whether they have failed or not. In fact, this is driven by safety, by performance more than anything else. And today, warranty-based designs is being driven by costs. How reliable are the finite element analysis softwares? A very good question. Finite element softwares have been there and the technology has been there for the last 55 years now. 45 years now. It got the finite element, the word got coined at the end of 1969. So the softwares became popular subsequently down the line. The analysis is only as good as the analysis is only as good as the person who is designing it. Imagine going for a headache issue to a doctor and the doctor giving you a pill to rectify your headache, and your headache persists and you go back and you do a scan, or we go and look at an angiogram for a block. The accuracy or the efficiency of the angiogram is only 70%. Unless the person is opened up, we really do not know how many blocks are there. That said apart, the reliability of the finite element predictions can be as high as 99% for deflections, as high as 95% for strains, as high as 80% to 85% for warranty calculations. Why 80 to 85%? In other words, if we say 4.5 years is the life of this particular design, then minimum life guaranteed over there is at least 4.5 years, if not more. Please share with us the problems you faced regarding gearbox failures, how you used FMEA in it. Very classic case of this is I can answer this question in a generic tone because we are constrained by confidentiality clauses with customers. we have had situations wherein 4 different gearboxes were supplied to the same customer. 2 of them failed, 2 of them did not. The same design has been used, same manufacturing processes have been used, same assembly process have been used, same material has been used, everything is the same, but still 2 of them failed, the other 2 did not. Why? Because of the variations in the tolerances that we have provided on the design, leading to eccentricity in the assembly of the gearbox, of the gears onto the shafts, leading to premature failure of bearings, leading to premature failure of tooth wear, leading to premature because of gear backlash, coming specifically as a result of tolerances. Now, can I include that, and can I do a finite elements to look at what is the level to which the vibrations would come? Absolutely. That's exactly where the design validation upfront helps us. I'll give another example. We are looking at, this is a classic example of a design in a gearbox. We are looking at breathers being used in gearboxes. We standardize fasteners across the gearbox products based on the breather design. Now, what if I ask you to come up with a breatherless design? You have saved the cost of that product, right? We can do the validation, look at it, and see how this can be improved. Another point, a gearbox comprises of a housing and a cover. When you take a housing and a cover and you have integrated them together, the stiffness of the gearbox is different. If you are looking at the casing separately with an open aperture when you are looking at a split housing for a casing, or when you are looking at one with a cover on top kind of design, then the stiffness drastically comes down because of an open and closed configurations. How does the stiffness help, especially with regard to the gearbox deflections, especially with regard to how it influences the backlash during operation? That's exactly where finite element validation comes of use, specifically with regard to gearboxes. And we have had customers facing problems primarily because of noises coming from the gearbox surfaces as attributed directly to the stiffnesses. Leakages is another example. Any other question? You have said that manufacturing processes can be simulated upfront. What kind of manufacturing processes? I'll give a very simple case of a sheet metal component being stamped together. We have what is called as thinning. Because of thinning, the section modulus gets reduced. Because of that, the life gets reduced. Because of that, our warranty clauses are affected. And thinning is something that comes from the blank size that is being fed for the stamping, the thickness of the raw material that is used. Typically, if the thinning leads to a problem, the design department comes back and says, oh, increase the thickness. The raw material cost increased. So how do we change it? How do we make sure that the durability problem arising as a result of a lower section modulus can be eliminated? It comes with a very simple analysis wherein you look at the blank sizes, you look at the feeding of the blank sizes. The little bit larger blank size will lead to more material going into the die, leading to protection of the wall thickness. Another example is the number of stages in stamping. These are all things which can be validated upfront before the depth to stretch ratio can be assessed upfront when we are coming up with low cost designs. When we are looking at alternatives, split designs can be put in instead of deep stampings primarily because of the thinning issue. These are all manufacturing design for manufacturability issues. We have very less lead time. We are not able to do analysis. Hence, we design using factor of safety. Is there any other procedure to follow? That's exactly what I talked about. We are talking about design for performance. Because we have very little time for design and we want to release the drawings as quickly as possible, we are releasing drawings without validating it. So where does the problem come in? The problem comes in if the order has been accepted at a lower cost because we wanted to win the order and the margins are thin and your serviceability cost goes up. It becomes a problem if the product has a recall at the customer's place and then you come back and revisit the design. It is not the amount of time that is spent in the design that is of higher emphasis. It is the amount of time in the overall product development that gets compressed as a result of good design practices that helps us to conquer better markets. So the factor of safety design, as I told you earlier, could be a feel-good factor, but it would always come back to haunt us subsequently down the line in terms of things gone wrong if we have to revisit the design, much more tragically if it is a customer reported problem. Kindly look at the service costs, the amount of warranty replacements that we have done that would justify the additional time in design to perfect the design before it is sent out. Otherwise, it will come back to haunt us. That is why these kinds of seminars are provided for helping our customers and people who are attending this program to understand that design is not a pushover. Design is centrality in the success of any product. For that, we need to validate those designs. Very simple example. We write an email, we write a report, we do a spell check on those reports or the emails before we send it. A spell check has to be done on our design. That's exactly where design validation comes in. Without a spell check on the design, it would affect the company's performance, growth, and sometimes even the viability of the organization. If we look at the amount of orders we have lost to competition as a result of pricing, you will see how lean and mean designs have to be coming about in terms of design for life. That's exactly where these processes score. This is what is adopted in the West. This is what is being adopted in mission critical areas in India. This is what we encourage our customers and attendees over here in this program to look at, revisit it, and give the emphasis that it deserves, because at the end of the day, the truth of the design lies in what is being practiced at the customer's place in terms of the costs to the end customer. Any other question? If there are no further questions, we thank you for attending this program. If you have any queries or you are interested more in seeing how this can be implemented in your organization, we would be happy to hear from you on info@egs.co.in or contact our office either in Chennai, Coimbatore, or in Trichy, and we shall be glad to assist you. And we would love to hear from you. Please visit our websites at egsindia.com and egs.co.in and leave your feedback, and we would be glad to hear from you to improve our programs of this kind. Thank you very much. Good day.